54. That'll be the anonymous quiz. If you haven't signed in yet, the 479557 is your code for signing in. All right. I'm going to just, I'm going to play the intro for my YouTube guys out there. So you're going to enjoy some intro. In the meantime, make sure everything else is running.
Somebody just said they missed the sign-in code.
Right here, 479557.
That's good. That might just be because you're not talking.
Yeah. Okay, so what I'm going to do now is we're going to kick this off. All right, so I don't have a cover screen for this, but anyway, so welcome to our session today is going to be on hazardous locations. Everybody on WebEx has been muted. For those who are on YouTube and on Facebook, thanks for joining us. We've got a big crowd today because we got a great presenter in Mr. Bob Potter. He's Eastern Region Field Application Specialist for Eaton's Crouse-Hinds business. He's been in the business for more than 24 years and very well published, engaged in IEEE, and this guy knows the code. He knows hazardous locations and equipment. It's a great mix, and I'm very happy that, Bob, you are with us today. So I appreciate you being here, and I'm going to let you take over on the slide deck. So I'm going to give you rights. I'm going to make you the presenter, and I'm going to let you take it away, and I'm going to watch chat, let everybody use chat. I'd appreciate that. And make sure your phones are on mute. And there you go. And you are ready to show off your stuff.
All righty. Thank you, Tom.
Not a problem. Thank you.
Everybody should be able to see my screen now. Obviously, if for some reason you can't, just please send out a chat. But as Tom had mentioned, I'm Bob Potter with the Crouse-Hinds division of Eaton. And this particular presentation today we're going to see is part of our Harsh and Hazardous Location Seminar series. We actually have 8 presentations that are available for CEU and PDH credits, but this presentation by far is our most popular one. This is the Hazardous Location Seminar. So with this particular seminar, what you're going to find is we're going to start right at the grassroots basic level. And the reason for that is everybody has different understandings or different comfort levels within working in hazardous location areas. So we're going to start right from the grassroots level and build from there. For those of you that have experience in hazardous location areas, I'm sure some of these points that we make will be a little bit of a review, but again, we want to make sure that we don't skip by something that could be very, very important, or there could be some things that somebody understands just because they were told, hey, it's like that, but now hopefully we give them a little bit of insight to why it's like that. So we're going to look at class, division, and group. And after we do a little bit of the basics overview, we're then going to take a further dive into class 1, the areas with the flammable gases, liquids, and vapors. For those of you that might be interested in class 2, we do have another presentation that does a deeper dive into the combustible dust. But as we're discussing the class 1 areas, we're going to look at the location of ceiling fittings. We're going to look at the different wiring methods that are available. And then we're also going to look at lighting and temperature rating concerns when selecting our luminaires. So right from the basics, what is a hazardous area? A hazardous area is an area due to the presence of flammable gases, liquids, and vapors, combustible dust, or easily ignitable fibers and fines can cause fire and explosion, breakdown and downtime, loss of production, repair and replacement, injury and death. Obviously, the last one is worst case scenario. We really want to avoid any injuries at all. Considerations for hazardous areas. Naturally, in a presentation like this, we're going to talk a lot about fire and explosion hazards, but there's some other considerations that we may have. Water, moisture, condensation. So when I'm looking at a particular environment, in addition to the NEMA 7 or whatever protection technique I'm using for hazardous location, I also want to be concerned about my environmental protection. Do I need to have a hose down rating, or is it an indoor application? So that's a consideration. Are there areas where moisture can collect in my conduit? So do I need to have a drain seal to allow that moisture to escape so I don't have an issue with my conductors getting damaged? And then condensation that can form inside enclosures. So those enclosures may have a breather and drain in them. And then, of course, anytime we have hazardous location areas, more times than not, it's going to be a corrosive condition. And one of the things I'd like to discuss right from the get-go is we do not work in explosion-proof areas. We work in hazardous location classified areas. It's quite common that times people will paint hazardous areas with a broad brushstroke, calling them explosion-proof. The problem is explosion-proof is actually one of the methods of protection. And if we paint hazardous locations with a broad brushstroke by just saying explosion-proof, we may get a product that's not the best suited product for that application. It could be a case where we get a particular product that is approved and certified, but it's an overkill, or we may actually get a product that is just flat out a code violation to install in that area. So for example, when I have an area with combustible dust, explosion-proof equipment is not automatically approved for a combustible dust area. There is some explosion-proof equipment that is certified for use also in a combustible dust area, but there is some equipment that contains certifications for only gases and vapors and not for combustible dust. So in that case, it'd be a code violation to use that in my combustible dust area. So again, explosion-proof is one of the methods of protection. We work in hazardous areas, we work in classified areas. In addition to explosion-proof, as far as one of the protection techniques, we also have dust ignition-proof equipment. That's going to be more for the areas with the combustible dust. We have factory sealing, purging, intrinsically safe. The 5 in the larger font are some of the more common protection techniques, but there's a number of others. There's gas detection systems, hermetically sealed, non-incentive wiring, and 40 others. Now, in order to have explosion, we need to have the 3 elements that make up the combustion triangle. We need to have our fuel. So in this case, it would be the flammable gas, liquid, or vapor. We need to have an oxidizer, and we also need to have an ignition source. And these elements need to be in proper proportion for there to be an explosion. Now, when it comes to combustible dust, the combustion triangle turns into the explosive pentagon. We still need to have our fuel. In this case, it's going to be the combustible dust. We still need to have our oxidizer. We also need to have our ignition source, but now we're going to add suspension, the dust in suspension and in containment. Now, for both the areas with combustible dust and the gases and vapors, we mentioned source of ignition. Some of the source of ignition are everyday things we see in our electrical lives, things with contacts that make and break, switches, circuit breakers, motor starters. But there's other ignition sources we don't always think about, sparking metals, heat can be an ignition source. For example, gases have an autoignition temperature. And at that particular temperature, the heat alone can be the ignition source for that particular gas or vapor. So we wouldn't need to have contacts opening and closing and creating an arc. The heat alone can cause that gas to explode. And then we also have static electricity. Now, I mentioned we need to have proper proportion for there to be able to be an explosion. When it comes to gases and vapors, here I'm talking about my lower flammable and upper flammable limits. With this particular situation, anywhere in between the minimum and maximum is a volatile mixture. If the mixture of gas to air fell to the left of the minimum, it would be too lean to be able to have an explosion. If it fell to the right of the maximum, it'd be too rich to have an explosion. And anywhere in between, as I said, it's going to be a volatile mixture. Now, depending on the particular substance, those upper and lower flammable limits change. So, for example, acetone is 2.5 to 13%, as compared to acetylene, which is 2.5 to 100%. So again, depending on the particular substance, those levels change. And those are the levels that are printed by NFPA, but there are some other factors that can possibly change the upper and lower flammable limits. If you had an area that was extremely hot or with extreme pressure, in that particular case, the flammable limits could open up slightly. Or if you had an area that was exceptionally cold, the upper and lower flammable limits could close in slightly. Now, when I'm looking at the upper and lower flammable limits, depending on the percentage, can affect the maximum explosion that you can have for that particular type of gas. When you're in the exact middle, it's going to be the optimum for the largest explosion that that particular gas or vapor can produce. The closer you get to the lower flammable limit or the upper flammable limit, it's going to weaken that explosion to a certain degree, and it'll also take more energy to ignite that particular gas. But don't make the mistake of thinking this is comforting, because a weakened explosion is still an explosion and can still injure and kill. Now, when it comes to the combustible dust, sometimes those people will still speak in the terminology of upper and lower flammable limits, but with combustible dust, what we're really concerned about is the minimum explosive concentration and the optimum explosive concentration. And just as we have with the gases and vapors, depending on the combustible dust, those particular concentrations can change as far as the explosive limits. Now, before we get into National Electrical Code classifications, I just wanted to take a moment. Tom, is there any questions at this particular moment that need to be answered?
All right, sorry about that. Is there a guide for testing electrical equipment in C1 areas?
Now, when you say testing the equipment to mean that it's still going to operate properly, I'm going to try and answer the question the way I think it means, but I could possibly be assuming the wrong intent of the question. When the equipment is originally tested by UL, it's designed to contain the explosion, which we'll talk about a little further in the presentation. When that equipment is tested, it's tested that it'll operate continuously and perform its function, providing that any maintenance and installation has been done correctly. When it is out in the field, you shouldn't need to do additional testing for the equipment.
Okay.
Now, if that wasn't exactly the way the question was intended, as we proceed forward, questionnaire, please, feel free to chat again and allow further detail, and we'll do the best we can do to answer that.
Sure. There's another question which I don't know if it's exactly on the same topic or the topic that we're on here, but it's similar. this gentleman was asking about lockout tagout requirements and verifying absence of voltages, and is it practical in a C1 area? How do you do? There's lockout tagouts on the outside of that of those equipment, right?
Basically, when you have your little background there, when you have your hazardous location areas, you still need to abide by all the other traditional rules that you would see within the National Electrical Code or the safety rules with maybe like an NFPA 70E. So you're going to be in a situation where you still are going to have lockout, tagout. Now, if the question becomes a concern of, well, I need to get inside the equipment, in that particular case, then a hot work permit needs to be obtained, and that hot work permit is basically the people in that particular area, maybe the process control people, the control room people, saying, yes, everything is okay in this Class 1 Division 2 area, you to go out, open that enclosure, and do those particular tests. Now, in a Class 1 Division 1 area, because we assume the gases and vapors are normally present, in those particular cases, often people will have some type of sniffer to detect if gas is present. And if not, then they can open up their particular enclosure and make any test or voltage readings or anything they would need to do with inside that unit. Oh, yeah. Okay, certainly. Alrighty. So as we started to allude to a moment ago, and whoever asked that question as far as the lockout, tagout, and everything, it was a perfect setup for this slide. But everything that we do in Chapter 5, the hazardous location articles, the previous articles of the code, Chapters 2, 3, and 4, all apply. So Chapter 5 is an extension of those particular code articles of what we need to do in addition for hazardous location areas. But everything in those first articles, or chapters, I should say, still applies. And the same thing happens when we're testing and having equipment certified for hazardous location areas. All the ordinary location tests have to be done first, and then the hazardous location tests are an extension of those ordinary location tests. One thing I'll also mention for those of you that may not be familiar, in the 2017 Code Edition, all the definitions that were in Chapter 5 were relocated to Article 100 with the other code definitions. Another thing that you might find, and a perfect example was in 2017, in Article 516, there were quite a number of changes in the spray booths and the dipping and coating process section of the code. So Article 516 uses a lot of extracted text. They do a lot of extracted tests from NFPA 33. So when you see brackets, that is actually extracted text that's being used in those particular areas. So that extracted text is taken word for word. So in the particular case in 2017, when you saw a lot of those changes, it wasn't that Code Making Panel 14 decided to do a lot of changes, but the people of NFPA 33 had made numerous changes. And since it was extracted text, then Code Making Panel 14 had to take word for word and put that into the Article 516. Another good thing that you might always want to check is what code cycle is the particular state where you're working in. Right now, Massachusetts is the only one that has adopted the 2020 code. That's not surprising because they tend to be first in the adoption. So this map, effective the beginning of this month, actually shows which particular code cycles the various states are on. But then the question becomes, who classifies the hazardous area? And that's a question that sometimes people are prepared for. Large companies often have a safety department for a department that was trained in classifying areas. Sometimes you'll also find the process chemical engineer. He may classify the areas because his education is in chemicals. You also may find sometimes an insurance company will have someone on staff that's capable of classifying an area. But I also do find that there's times that the electrical engineer will have the classification dropped in their lab. And so there are some areas that you can further go for information. When you're looking at NFPA 70, some of the specific applications, which are articles 510 through 516 that cover gas stations and aircraft hangars and spray booths, they'll give exact information as far as classifying. But unfortunately, the lion's share, the majority of our applications don't fall within those articles. So a place that you might want to go is NFPA 497, the recommendation for classification of areas containing flammable gases, liquids, and vapors. Will also fall within gases, those liquids, and vapors. API 500 for combustible dust, NFPA 499. So there's various areas you can go for further information as far as classifying of areas. But once we know what our classification is, we're going to want to start selecting material. So class 1 is our area with flammable gases, liquids, and vapors. Class 2 is our area with combustible dust, and class 3 is easily ignitable fibers and flyings. So sometimes people think these areas are, these particular classes are ranked in the order of danger. Nothing could be further from the truth. When you have an area with the gases and vapors, that's going to be an explosion followed by a fire. Combustible dust can often be multiple explosions followed by the fire. In a combustible dust area, it's not uncommon to have a primary explosion, the initial explosion. And when that initial explosion happens, it shakes the building. And dust that had become settled now becomes airborne. And that dust in suspension will ignite. Secondary explosion. And sometimes you can have a series of secondary explosions. And then class 3 is your easily ignitable fibers and flyings, cottons, rayons. These particular substances aren't quite as likely to be airborne. So in this particular case, it's often a flash fire, but they all can be very dangerous and they all can create injury and kill. But the next thing we're going to want to know is our area Division 1 or Division 2. So Division 1 is considered hazardous under normal operating conditions. Division 2 takes a fault condition to become hazardous. So an example would be if we had a paint booth and we were spraying the piece of equipment that were in the paint booth. Under normal operating conditions, those spray vapors are going to be present. So that'd be a Division 1 area. Now, maybe next door is an area where they're storing a lot of the pigments and chemicals and paints that are used in that spray painting application. And for that particular area, one of those canisters or drums would have to leak for the gases to become present. So it would not normally be hazardous, it would be a fault condition for those particular gases to become hazardous. And then we're going to want to know what is our group. So under class 1, we have groups A, B, C, and D, and this takes a little closer look at the explosive properties of our gases and vapors. Groups E, F, and G under class 2 take a look at what type of combustible dust do I have in that particular area. Now, there are times that you may possibly see a nameplate that does not signify division. And so the top pictorial that you see there is a perfect example of that. It just says class 1, and then it has the groups that this particular piece of equipment has been approved for. Whenever you see a nameplate that says class 1 and does not signify a division, it is approved for division 1. Technically, the code only requires you to mark a product for division 2. So you see the bottom pictorial has our class, it has our division, and it also contains the groups that that particular product has been approved for. Now, this is a little bit rarer as time goes on because a lot of manufacturers have begun to understand that that why the code doesn't require you to write Class 1, Division 1, it does create some confusion. So this is something that you're not quite seeing as often as much as you used to. So now we're going to take a little bit closer look at the area with the flammable gases, liquids, and vapors, our Class 1 area. So when I have a Class 1, Division 1 area, here it's assumed that my gases and vapors are present under normal operating conditions. So when I have this particular area, we're concerned about the gases and vapors that are able to migrate into my electrical products. And we can't prevent this. Conduit threads breathe. When items heat up and cool down, you get vacuum effects. So when I'm at Class 1, Division 1 area, it's assumed that the gases and vapors have migrated into my raceway, into my luminaires, into my receptacles, my switches, all of my electrical equipment. Now, Class 1, Division 2, again, here is going to be a fault condition for the gases and vapors to become present. Or also, you might have an area that would have normally been Class 1, Division 1, but through positive ventilation, changes of air, the particular area may possibly be able to be derated to a Class 1, Division 2 area. And then whenever I have my Class 1, Division 1 area, you're typically going to have an adjacent area that is Class 1, Division 2. So if I get back to the paint booth example, that's going to be Class 1, Division 1. And with that particular application, a 3-foot envelope in every direction outside the door of the paint booth is going to be Class 1, Division 2. Now, not every envelope is always 3 feet. It just depends on the particular application. So, for example, a gas station, we stop at them, multiple times a week to put gas in our car. When we pull up to the gas station, 18 inches on each side of the pump is a Class 1, Division 2 area. 18 inches up from the ground in a 20-foot diameter out from that pump in all directions is a Class 1, Division 2 area. And a sump underneath of the pumps would be Class 1, Division 1. So here's a perfect example where in that particular application, the envelope of the Division 2 area is different than what it is with the paint booth example. And then we're going to look at our groups. Class 1 has groups A, B, C, and D. A is acetylene. B is your hydrogen-based gases, 30% volume or higher. C is your ethers, your ethylenes. D is going to be gasoline, propane, methane. And these particular group order, you can actually make the argument are ranked in the order of danger. For example, acetylene is easier to ignite and a much more forceful explosion than ethylene. Or hydrogen, for example, is going to be easier to ignite and a more forceful explosion than propane. So when a manufacturer is producing the equipment to be used in hazardous location areas, it's extremely important for us to understand what these particular gas groups are to make sure that that particular piece of equipment has been approved for that area and will operate safely in that area. And the reason for that is that explosion-proof enclosures, when we're using the NEMA 7 explosion-proof protection technique, they contain the explosion, cool the hot gases, and then harmlessly release those cool gases back out to the atmosphere. So we need to make sure that when we have this particular unit containing the explosion, that the gas group that's exploding inside or could explode inside is approved for that unit so the unit doesn't rupture or fracture when it's containing the explosion. So sometimes when manufacturers are determining and looking for approval for a particular gas group, they may change thread pitching for the particular product. You may have material walls thicker. There could be volume of gas concerns within the particular unit. So there's different aspects that a manufacturer looks at when they're looking to have a particular product approved for a particular gas group. Now, the way we make sure that these units are not going to rupture or fracture is through the UL 1203 test. This is sometimes called the 4x safety factor test. And what we perform with this particular test is we determine what particular gas group we want to have this product approved for. And then we develop what's the maximum explosion pressure that can happen inside that enclosure. Then that maximum internal pressure with a hydrostatic test is done to 4 times that original internal pressure. So we take the internal pressure from the thermal explosion and a hydrostatic test to 4 times that amount, and that gives us that 4 times safety factor to ensure that when this unit is containing an explosion, it can't rupture or fracture. And as long as the unit has been installed properly, or any maintenance, opening the enclosure and closing it back up has all been done correctly, these units can actually last decades of performance operating correctly. So I have a particular unit that is a threaded flame path. Here, this unit is going to contain the explosion, and the time it takes for the gases to pass over the threads with the metal acting as a heat sink is going to cool those threads and then harmlessly release them back out to the atmosphere. Now, there's something else that takes effect, the Joule-Thomson effect. Sometimes people will affectionately call this the refrigeration effect. And what this is anytime something passes from a high-pressure system to a low-pressure system, there's an additional cooling. An example I could give to you would be the air that's in the tire on your car. When you push on the valve stem, the air that's coming out seems cool. That's because when it's in your tire, it's under high pressure. And when it comes to that valve stem, it's under high pressure. But as it exits the valve stem, it's transitioning to a lower pressure. And that's why you feel that additional cooling. Now, a very popular unit also in hazardous location areas is the flange joint, the ground joint. This is popular with control stations, motor starters, panel boards, these types of products in hazardous location areas. And with this particular product, rather than the thread being the flame path, the flange is the flame path. So we're going to make sure that when we're installing this product, the flange is free and clear of any dirt, any damage, and we're going to want to make sure we have all bolts installed. And that I can't say enough, all bolts installed. For a control station such as this, typically people aren't questioning the installation of the bolts. It's only 4 bolts. But when I get to the larger units, the large junction boxes, the motor starters, the panel boards, and we start seeing 20, 30, 40 bolts, here's when I get people asking the question, can't we just put 1 bolt in each corner? I'm getting in and out of this unit, and I'm tired of opening and closing all these bolts. Well, these bolts maintain the flame path integrity, and without them, the gases could escape hot and ignite the surrounding gases and vapors and cause a large explosion within the facility. So as you can see here, it's also extremely important if a bolt is broken or missing to replace it. Now, some manufacturers have captive bolts, so this isn't quite as much of an issue. But for the manufacturers that don't have captive bolts, it's very common for the person working on the unit to take out all the bolts and lay them on the ground. So if one were to become missing, it's important to contact that manufacturer to have it replaced. So now we're going to see a little bit of a video that shows how NEMA 7 enclosures work, what can happen if you have bolts missing. And while this particular video does mention our name, it has been approved for the continuing education curriculum because it's really a teaching video. It's not a commercial video. So the information you see with this video would be true across the board for all particular manufacturers in hazardous location areas. Just want to confirm that the video Understanding Explosion-Proof Enclosures is visible on my screen or on your screen? Perfect.
When it comes to explosion-proof enclosures in harsh and hazardous environments, failure is simply not an option. When it does occur, the consequences can be devastating. Because gases and vapors present in Division 1 and 2 areas will commonly enter explosion-proof enclosures, the NEC and CEC have set specific requirements regarding their design and installation. All NEMA 7 rated enclosures are constructed to withstand and contain the internal combustion of gases and vapors. They're also designed to cool those hot gases down before releasing them into a hazardous outside atmosphere. This is accomplished via machined flame paths or joints. Properly installed, explosion-proof enclosures are very safe and often deliver decades of reliable service. Traditional NEMA 7 enclosures are designed with a significant number of cover bolts. When fully engaged, these bolts apply even pressure around the enclosure's flame paths, allowing heat from an internal combustion to be transferred evenly over the paths and released safely back into the atmosphere. This test, conducted at Eaton Crouse-Hines Business UL Certified Lab, shows a traditional NEMA 7 enclosure successfully containing an internal combustion, cooling the explosive gases, and preventing the outside hazardous atmosphere from igniting. Watch again in slow motion as the enclosure withstands the combustion forces and cools the explosive gas by diverting it through all the engineered flame paths. However, instead of properly securing all enclosure bolts, some installers believe that randomly installing and tightening just a few of them is good enough. But watch what happens when this seemingly minor step is skipped. For this test, we secured all cover bolts except one. As you can see, when a spark ignites the hazardous gases inside the enclosure, this one missing bolt allowed the burning gases to escape before being properly cooled. The result? The hazardous gases outside the enclosure are also ignited, causing a significant secondary explosion, which can lead to equipment damage and injury or death to personnel. Watch in slow motion what can happen in a flash.
So it gives you a good idea the importance of maintaining the integrity with these particular enclosures. I just want to make sure that everybody can see that we're back to the presentation. Perfect. Okay. Now, we mentioned the UL 1203 test as the 4-time safety factor test, but another thing that UL 1203 provides is a baseline for our fault current rating. So the particular hazardous location NEMA 7 enclosure has a baseline fault current of 10K AIC. Now, what happens is if an application comes up and somebody wishes to achieve a higher fault current rating because of the available fault current that had been calculated, maybe they need 14K, 35K, 65K, whatever the particular fault current rating that is possible for that particular equipment. In hazardous location areas, people will just sometimes put a higher rated piece of equipment in there, maybe a higher rated fuse, a higher rated circuit breaker, but the unit will still only be rated 10K. So it's going to be our weak link between the internal component and the enclosure. So the nameplate is still only going to say 10K. And the reason for that is that when the unit is tested for 1203, it's tested with a spark plug. That replicates the thermal explosion that you have with contacts opening and closing. But when there is an explosion caused by fault current, here, in this particular case, there's also electromagnetic effects that happen inside the enclosure. So you get that attraction and repelling with the electromagnetic effects, and that affects the flame path differently. So to have an entire unit rated for the particular AIC rating that you require for that project, the manufacturer needs to test to UL 2062. So in this particular case, the internal components can be installed, matching the required AIC rating, and the enclosure will also be approved for that particular AIC rating. Now, when it comes to wiring methods, in Class 1, Division 1, threaded rigid metal conduit. So it can be my rigid steel, rigid aluminum, stainless steel, also IMC, MI cable, extra hard usage cord. You know, when we have things such as plugs and receptacles, we need to have some flexibility. So the code says extra hard usage cord. What is extra hard usage cord? Like an SO cord, an S cord. And in fact, a lot of the manufacturers are putting this terminology, extra hard usage, at the top of their catalog pages for those cables that can be used in hazardous location areas. But then in 1996, we started seeing some influence from the IEC world on our National Electrical Code, because the IEC world does a lot of open cabling, where here in the United States, we tend to have a lot of conduit systems. So in 1996, the National Electrical Code said if you have a jacketed MC cable and it's tested and listed for Class 1, Division 1, uses a cable gland that's also tested and listed for Class 1, Division 1 in an area with limited public access, this product was now a new wiring method. And then in 1999, they added instrument tray cable with the HL designation for Division 1. And then in 2014, the tray cable exposed run. In 2020, Type P with the metal braided armor was added as a Class 1, Division 1 wiring method. Now, when it comes to Class 1, Division 2, all of my Division 1 wiring methods are approved and actually sometimes required. If I were to have an explosion-proof motor starter in my Class 1, Division 2 area, the raceway between that motor starter and my ceiling fitting has to be the Division 1 wiring method. After the ceiling fitting is when I can start using the less stringent Class 1, Division 2 wiring methods, where you may see things such as liquid tight, flexible metal conduit, enclosed and gasketed wireway. You'll notice my cables no longer have the HL designation, which was the designation for Division 1. Now, when we're working with our conduit, there are times that you're going to want to be able to make sure that it threads easy enough, or if you have junction boxes with threads, you're going to want to have some assistance in threading, especially if it's copper-free aluminum, because you can have the threads bind up on you. But what you cannot use is that plumber's on tape. Manufacturers do have products that are approved for use with their particular equipment, in which these have been tested. Typically, these products are non-petroleum based, so they're going to maintain your bonding and grounding, but they're also not going to be a possible ignition source. Now, when I'm in an area that is Class 1, Division 1, and I'm using the explosion-proof protection technique, my boxes and fittings are required to be explosion-proof. When I'm in Class 1, Division 2, anytime I have an item that is an arcing source, a motor starter, circuit breaker, relays, here, that equipment is also going to be explosion-proof. But if I have items that are non-arcing, such as a splice box, a terminal housing, those particular enclosures and fittings are not required to be explosion-proof. And what we're saying is that in my Division 1 area, my gases are normally present. My arcing source, we're going to call it the combination motor starter. If that motor starter operates, my gases are present and explosions, so I need that explosion-proof equipment. Now, remaining in my Division 1 area with my gas and vapors present, my non-arcing source, box. Here, one fault condition, I can have an explosion. So I need to have explosion-proof equipment. Now, as I move over to Division 2, here my gases aren't normally present. But what if they become present and migrate into my motor starter? I could have an explosion with that one fault condition. So I need that explosion-proof equipment. Now, remaining in my Division 2 area with my terminal box, now I need to have two fault conditions. And really, these fault conditions need to be in the same time frame. An area where gas wouldn't normally become present would have to become present. An item that wouldn't normally arc would have to arc. And so because of that, in that particular application, the National Electrical Code says that my boxes and fittings are not required to be explosion proof. And this is Article 501.10B4. Now, that particular article tells the story slightly different than I do. That particular paragraph says boxes and fittings are not required to be explosion proof except for, and then they give you 3 other code references. When you look up those 3 other code references, it is the arcing sources. So the code tends to tell the story a little bit from the bottom up. I just find it a little bit easier as we're going through the different scenarios to tell the story bottom down or top down. But in the end, it's the exact same thing. And in the end, what it means is that in those particular applications in Class 1 Division 2, you might see the everyday conduit body used, or you might see enclosures that are non-rated NEMA 7 enclosures used. That could be enclosures just designed for the environmental protection. You might see terminals inside. You might see FS boxes just being used as splice boxes. Or there may be times that you see products such as control stations where a manufacturer might say this product is Class 1 Division 2 and it's in a non-metallic housing or a stainless steel housing, a housing other than the traditional explosion-proof NEMA 7 housing. And that's because what they've done is they've used an encapsulated or factory sealed contact block. When you do that, it takes the item from being here and drops it down here, just being concerned with the terminals. And so that's why that item doesn't have to go in the explosion-proof housing. And that's only Division 2, not Division 1. Now, there are times that you may find that you come across zone-rated equipment. Zone-rated equipment is a parallel, the IEC parallel for division classifications. And we do allow for zone-rated equipment under Article 505 for gases and vapors and Article 506 for our combustible dust. And there are times that the zone-rated equipment may be used in my division areas. So if I have an area rated Zone 0, Zone 1, or Zone 2, I may use that equipment in a Class 1 Division 2 area, provided it's approved for the proper gas group and any applicable temperature ratings as necessary. And product that is approved for Zone 0 may be used in a Class 1 Division 1 or Class 1 Division 2 area, providing I have the AEX marking. What the AEX marking assures is my ordinary location requirements have been met. And you remember I mentioned earlier that Chapter 5 of the National Electrical Code is really an extension, the hazardous location extension of the previous articles, but it still has to pass all the requirements of those particular ordinary location articles. And it's no different for the equipment. So if you were to have a facility and you had a piece of equipment coming in from overseas, and that particular equipment would be not containing the AEX marking for zone or not containing a division rating, it may be approved for hazardous location, but we don't know that it's approved for ordinary location. So we don't know if a component inside, such as a circuit breaker, has passed the UL 489 test, or we don't know if the non-metallics has passed the UL 94 flammability test, or if the conductors have passed our particular UL test. The AEX marking ensures that. One other addition, Zone 1 equipment may never be used in a Division 1 area. There's a difference in certification, a difference in testing, a difference in that so-called safety factor that I had mentioned previously. So Zone 1 equipment may never be used in a Division 1 area. Tom, this might be a good place that we can answer any questions. And also, if you wanted to review the quiz at this time. I think I did see a question come up as far as temperatures with a negative 25.
Oh yeah, it just came up. You want to take that one? If you see it, what are the normal operating temperatures
Sure.
that Haslock equipment is tested for use in? I think it's minus 25 through plus 40, but take it away.
Yeah. So when another thing with the zone equipment, that tends to be tested for negative 20, where our standard testing here with the 4-time safety factor under UL 1203 is going to be the negative 25 through 40 degrees, plus 40. Now, if the area is an area that's going to be colder and the equipment is being tested for something colder than negative 25, UL does perform tests for that, but then it becomes a 6-time safety factor test as opposed to the 4-time safety factor. On the other end, when we're at the 40 degrees C, that is my standard baseline testing. If I have a product that is a heat-producing product, and that product is going to be used in an area that is in warmer climate, I have to make sure that that particular product has been approved for that warmer climate, because that can affect the temperature ratings. So in that particular case, the code requires me to mark that additional temperature, whether it might be 65 or 55 degrees Fahrenheit. The code's going to require a marking of a TA or a TAMD and that particular temperature.
Excellent. So this is another good question, Bob. It was on the WebEx.
Sure.
WebEx. How do you classify a pipe carrying flammable liquid? Do you classify only the areas where there are breaks, or do you classify the whole pipe regardless of breaks or no breaks?
And that is, with our functions within manufacturing companies, we don't classify areas. There's a lot that goes into classifying areas. You need to be familiar with static electricity. You need to be familiar with the Automation Society. You need to be familiar with lightning hazards. The code used to actually call out recorded industrial experience. Plus, there's also things such as we mentioned earlier, where if you have extreme heat, you may have a particular scenario where the upper and lower flammable limits changes. There's a lot that goes into classifying an area. Is the substance heavier or lighter than air? Is it going to stay at the ground or float upwards? So that's really where you're going to look at documents such as, API 500, which is the American Petroleum Institute, NFPA 497, and they're going to give you the guidance in the classification of those particular areas. Now, I can tell you that there have been some recommendations that people have been making with API where they're suggesting you classify certain bubbles. So you would have bubbles that might be all these Class 1 Division 2 bubbles, and then some non-classified areas in between. That might lend more to the classifying of maybe the joint area where the pipe is. Most of the refineries that I've seen haven't really subscribed to all these fragmented, smaller Division 2 areas. They've stuck with classifying a larger overall area as Class 1 Division 2, because in that particular case, they don't have to worry about if a process changes, if something changes where the area that needs to be expanded with the Division 2 bubble. In that particular scenario, they've already deemed it Class 1 Division 2, and they have already addressed it with the particular equipment that's installed in that area. But really, the particular documents that guide you in the classifying of areas are going to a lot of times give you not only the documentation, but pictorials too to help guide.
All right, perfect. So let me ask you a question, just my own edification here.
Mm-hmm.
That does it matter, like if that pipe, if that fluid is in the type of fluid or the type of pipe that it's in, whether it's a rubber or if it's something that could be easily penetrated, if it's a steel pipe, what is there? Does it matter the material that vessel is made out of?
Not that I've ever found with the particular scenario. And again, there could be someone that is in a refinery that might have a little bit more insight to that than I do, but I have not seen that particular scenario as far as a particular pipe being the difference.
All right, perfect. All right, so here's another one. Mr. Randall on YouTube asked the question, similar to what is referenced in 505.20 regarding the suitability for Group 2C equipment. Does IIC, is it Roman numeral 2? Is that, am I reading that right?
Well, yeah. That is a category within the IECEX method. If you were to see a 1, that is for mining. The 2 is the gases other than mining. It's typically sometimes referred to as the industrial type of gases. And our National Electrical Code doesn't get into mining, but the IECEX world does. Now, when you see that C, that is their gas group, but there's a difference of the particular material groups when compared to our National Electrical Code. For example, we have A, B, C, and D, but when it's the IECEX world, and you'll also see this in our Article 505, C now becomes acetylene and hydrogen. B becomes your ethers and ethylenes. A becomes your gasoline, methane, propane. Now, here in the United States, we have a preference to break apart acetylene and hydrogen. So we'll often do 2B plus H2. Now, we do have a whole presentation that is available for the IECEX and the comparison of IECEX worldwide to here in the United States, and also for the ATEX certifications. And that's another presentation that if there was interest, we could always do on another day for presenting that. And a lot of these particular scenarios get covered in that presentation.
Okay, so what I did was I added his question into the chat because rather than me try to read it, I don't know, can you read it? Can you see it? It says, it starts with similar to what is referenced in 505.20.
I cannot see it at this moment.
Okay, I'll read it to you. Similar to what is referenced in 505.20 regarding the suitability for Group 2C or IIC equipment in 2B/2A, Roman numeral 2B and slash Roman numeral 2A, and IIB in IIA applications, why does the NEC not reflect Group A's suitability for B, C, etc.?
Okay, so in the IEC, when you have something that is the 2C, that also covers the 2B and the 2A. Yes, under our traditional division articles, we would put everything. So if it was good for groups A, B, C, and D, we would put A, B, C, and D. But in the nomenclature in the IECEX world, they don't do that. So a lot of what you see in our Article 505 and 506 has really been taken from the way that the IECEX world does their nomenclature. Now, that doesn't mean there's not some differences, because there's differences with the ATEX, the European community, in the way they mark, and there are some differences with our material here in the United States, the way we mark. But there is a lot of similarities worldwide with the way the markings are done. It gives it a certain amount of uniformity.
Okay, I got another one here from Don Gannier. When you get to seals, I'm not sure if you're there yet, but he says, can you comment on the change in the 2020 code that specifically permits the use of standard conduit couplings between an enclosure that requires sealing and the sealing fitting? He says he can find no evidence that those couplings have ever been evaluated for containing and slowly releasing the hot gases from the explosion. The straight threads on the conduit coupling do not have the tight fit like the threads on equipment that has been evaluated for containing the explosion.
Yeah.
Can you comment on that one?
And yeah, that was actually not as much of a change, but more word clarifications, because the coupling had been in previous code scenarios. And what happens is, and we'll also be discussing this a little further in the presentation, if I were to have an explosion-proof enclosure and I have a ceiling fitting, the code does allow me to put certain explosion-proof fittings in between the ceiling fitting and also the enclosure. It can help facilitate repair and replacement. It may be because of an obstruction. There could be a number of reasons for that. And so the fittings, though, do need to be certified rated fittings. Now, my normal rigid conduit and those particular couplings are certified. So in other words, you don't necessarily see when you pick up a piece of rigid conduit, Class 1, Division 1 written on it, but that is an approved wiring method. And those couplings that you were to see that go in conjunction with those are approved for a wiring method in Class 1, Division 1 and Class 1, Division 2. But the other fittings that you would put in there, whether it's a reducing bushing or whether it's a capped elbow or something along that line, they are required to be certified.
Perfect. And we got one more from Gary Beckstrand. I'm not sure, I don't know how this involved this with you, but he says, please address electrical installations when diesel fuel is used, such as in a healthcare facility.
Okay. It's an interesting thing is when you look at NFPA 497 and they show you the different chemical substances there, diesel is not actually listed as a unit, as a type of substance that can explode. And so I've actually seen projects where, say transportation companies, and they have buses that are operating on both gasoline and diesel. And the local authority having jurisdiction for those repair areas has required the ones for gasoline to follow Chapter 5, Article 500 and 501 of the National Electrical Code. But for those areas that can accept the diesel buses, they've allowed them to have that remain non-classified, providing that they make sure that only a diesel bus would ever go in that lane, that particular repair garage, and a gasoline bus would never go in that particular repair garage.
All right, perfect. So what I'll do now is I'm not going to share my screen because I don't want to cause a problem. What I'll do is I'll read the question, and I'll tell you how many people chose one answer over the other, and then you can let us know which is right. All right.
Sure.
All right. So the first question, is explosion-proof material is automatically approved for all hazardous classified locations. And it was true, false, and not sure. We have 19 trues, 146 false, and 12 not sures. What do you say?
They always say there's a safety in numbers, and the 146 are correct. This was discussed when I had the picture of the refinery up on the screen. And the scenario is explosion-proof equipment is one protection technique. But when it comes to an area with combustible dust, if the particular equipment is not certified for combustible dust, that explosion-proof equipment is not permitted in that area. And that can be found in Article 502.5 that states that.
Right. Perfect. So let me hit the next one.
It doesn't state it. I paraphrased it, so the wording is going to be slightly different than the way I phrased it, but that's what the article that tells us.
Perfect. So okay. So that was 146. That was like you said. It was. It's good in numbers. So let me go to the next question. If I can find out how to do it. We had 178. We have 178 respondents, just to let you know. So here's the next question.
Yeah.
There are NEC allowances for a non-classified enclosure to be installed in a Class 1 Division 2 location. True, false, and not sure. We have 110 true, 38 false, 23 not sure. So who's right, the 110 or the 38 plus the 23?
Safety in numbers again. And this gets back to that 4 square that I just had on the screen that showed us when I have the Class 1 Division 2 area, and it's a non-arcing, a splice box, a terminal box, that particular piece of equipment is not required to be explosion proof. And that's where a lot of times in chemical plants, refineries, wastewater treatment plants, where you may see regular everyday conduits or regular everyday junction boxes installed. And that's Article 501.10B4.
Perfect. So I'm going to go to the next one now. So we had 111 people that are okay. Okay, now this one's a little bit more split. I like this. So we have a true, false, and not sure. Before I read the question, we have 72 in the true, 38 in the false, and 57 in the not sure. So we're going to teach somebody something on this question. The question is, the NEC allows for IECEX zone rated equipment to be installed in the United States. Is that true or false?
And it is true, providing it has the AEX marking in it. We have Article 505 that is set up for gases and vapors. We have Article 506 that's set up for the zones for combustible dust. And as we reviewed shortly ago, where the zone equipment may sometimes be used in division areas. So in this particular case, it is true, but I could see that some people might possibly say false in saying that, well, you said IECEX and you didn't say it has to have the AEX marking. So there could be a chance that some of those people that have false know exactly what they're talking about, but maybe I needed to be slightly more detailed in my question.
Well, that's perfect. That's the way that is the way that cookie crumbles. So that's good. That's okay. We can live with that one. All right, we're gonna do the next one. So what I did was I just moved the I moved the Mentimeter thing so the guys on the web can see it. I forgot I'm projecting, so I can do that.
Yeah, that last question could be a case where maybe I could have worded it slightly better.
That's fine. Okay, so this one here, we've got 121 say true, 13 say false, and 33 have no clue. And the question is, a pendant mount fixture luminaire with pendant exceeding 12 inches must either be braced against lateral displacement or have a fitting providing flexibility. Is it true? Is it false?
And that is true. The permanent effective brace, as the code likes to say, needs to come down and connect on the pendant stem within 12 inches of where that stem connects to the luminaire. In the case of the flexibility needs to be within 12 inches of where that pendant stem connects to the junction box.
Awesome. All right. So we have 123. That was consensus by majority too. So that was good. Okay. So this one is again a little bit more split. So we have about 80 something people who aren't sure, and we have 80 people that say true. So we have 80 true, 56 false, and 29 not sure. We're going to teach somebody something on this one. The standard ceiling fitting is approved for 40% cross-sectional area of conductors conduit fill. True or false?
And that is false. The code tells us that your ceiling fitting is approved for a 25% cross-sectional fill unless specifically approved for a higher fill rate. So that's where you would have manufacturers producing the expanded fill ceiling fitting, which gives you that 40% fill rate.
Excellent. Well, that means 81 people just learned something, and the other 29 as well. So, all right, we're going to go. I don't know if that's the last one or if there's another one. Let's just double check. Yep, that was the last Mentimeter quiz. And I'm going to just check to see if anything else came in on YouTube. There's some discussion about diesel. There's diesel's not classified fuel. What else? Mr. Randall, I'm going to double check over here. When you get to seals, we already talked about that one. Similar, I already talked about that one. But that's the point. No, AX. So there's some dialogue going on, which I love. What I really like about the chat is people start answering each other's questions, and you got some good dialogue going on. So that's a good thing. So I don't see anything else over there, Bob. I'm not sure.
Okay, so why don't we continue on then?
We will do that. I'm going to move my chat
Alrighty.
stuff over, and you can take it. Let me mute myself. You could take it away. Thanks.
Certainly. All right, here we go. So ceiling fittings, probably one of the most important yet misused and abused and misunderstood items in all of hazardous location areas. Ceiling fittings are designed to minimize the passage of gases, vapors, or flames from traveling through my conduit system. It's going to limit the explosion to the enclosure. So that enclosure will do what it was designed to do: contain the explosion, pull the gases, harmlessly release those back out to the atmosphere. And it's going to prevent pressure piling. In other words, when there's an explosion in the first enclosure, not all of the gas and vapors will explode right away. You're going to have that particular explosion start traveling through the conduit system, and the gas is going to compress, and it's going to pressure pile, compress into the next enclosure. And that enclosure then would have more gas in it than it was designed to handle, and that next explosion would actually be larger. So the ceiling fitting is going to prevent pressure piling. Seals are not intended to prevent the passage of gases and vapors at a differential of pressure. In other words, if you were to put the water on top of the ceiling fitting, sooner or later it's going to migrate down through the fitting. And where this becomes important is in the process seal applications, and that's covered under Article 501.17 of the National Electrical Code. But for today, we're really going to be focusing on more of the standard applications for sealing and not that process seal or secondary process seal application. So our sealing can be done in a couple of ways. One is the external sealing fitting, and then another is factory seal, where the sealing is done integral to the electrical equipment. Now, it's very, very important to make sure that when we pour the sealing fitting, we separate the conductors with the fiber and pour in our cement compound. So here's an example of the fiber that separated the conductors properly. So the compound was poured around each and every single conductor. Here was an example if somebody just grouped the cables together in a bundle and then poured the compound, it would just go around the outside. And here's an area where gases and vapors could escape right through where all those circular edges come together. And so that would be an incorrectly poured fitting. The gases could migrate through my conduit system. The explosion could travel through my conduit system. So it's critical for the safety to make sure that we have each and every individual conductor separated and the compound is around each one. Also, these units are all tested by UL as a complete assembly. So if you were to have a compound that was being used with a different manufacturer sealing fitting, so for example, if ceiling fitting A wanted to use the manufacturer B compound, you would actually have to see if that ceiling fitting has been tested to go with that particular compound. The code tells us that the ceiling fitting shall be listed for one or more compounds. So if it's not listed for use with that particular compound, then that compound could not be used in that fitting. My recommendation is if you use manufacturer A for ceiling fitting, use manufacturer A for the compound. If you use manufacturer B for the ceiling fitting, use manufacturer B for the compound and fiber. Essentially, this unit is going to contain the explosion. The flame path is going to allow those cool gases to escape, and the explosion is going to want to be traveling in our conduit, and this ceiling fitting is going to make sure that it doesn't continue to travel down. It's going to minimize the effects of those gases and vapors. So where do these ceiling fittings go? Because I've seen many applications where Ceiling fittings are placed everywhere, including areas that don't necessarily need a ceiling fitting. And then I also see where ceiling fittings are sometimes missed in areas that they should have been placed. So when I have an arcing source, we're referring to the top pictorial here, an arcing source such as a motor starter, that when it's installed in a Class 1 Division 1 or a Class 1 Division 2 area, each individual conduit entering and exiting is required to be sealed within 18 inches of that unit. And then in 2017, the National Electrical Code added a new statement, or as required by the enclosure marking. And that is because there are times that some manufacturers will have ceiling fitting requirements that are more strict than the National Electrical Code's 18-inch rule. This is how they would achieve passing part of the UL 1203 test. So in this particular scenario, if it was listed in the instructions or in their catalog, it would be easy to miss that the ceiling fitting needed to be in a position that was closer than the 18 inches. So now it's required to be marked on the nameplate, right on the enclosure, so the installer knows that that ceiling fitting needs to be in a different position on that particular enclosure. Now, when it comes to Class 1 Division 1 and Class 1 Division 1 only, I'm looking at the bottom pictorial now. When I have a product that is housing splices or terminals, I'm required to seal conduits 2 inches or larger. So the top pictorial is arcing sources, both Division 1 and Division 2. The bottom pictorial is only Division 1 splice boxes. Now, the reason that this is not Division 2 also is because, as we saw earlier, if I have a splice box that's in Class 1 Division 2, it's not required to be explosion proof. So putting a seal within 18 inches of that particular non-hazardous rated box gets me no further integrity. So it's not required. Now, this is one that we started to allude to a little bit earlier with the question. And here is where the National Electrical Code tells me that I may put certain explosion-proof or rated fittings between the explosion-proof enclosure and the ceiling fitting. My 18-inch rule still does apply. And up until 2017, the code also used to say T's and L's, but that was actually eliminated in 2017. Now it's unions, couplings, reducers, elbows, capped elbows, not larger than the trade size. So in this particular scenario, the union is very, very popular because it facilitates repair and replacement of the electrical equipment, especially when it comes to instrumentation. Instrumentation seems to need to be repaired quite often. So in this particular scenario, if you have the union, which is really the three-piece coupling for hazardous location, in that particular scenario, if it was you had your device, you just simply undo your conductors, unscrew the three-piece coupling, take the device off, repair or replace it, bring it back, and just rescrew the three-piece coupling together. Also, if you have units that have feed-through hubs and you didn't have unions, the only way you were going to be able to take that unit off the wall or out of that conduit system would be to cut the conduit. But by having a union at the bottom and a union at the top, each end, you disconnect your conductors, unscrew each union, and then simply just pull the product away from the conduit, and then you repair or replace it. Now, when it comes to boundary seals, here we're making sure that the gas does not migrate from one classified area to a lesser classified area. So my boundary seal can be on either side of the boundary, but must be within 10 feet of the boundary. And once I put in that boundary seal between the boundary and that ceiling fitting, I can have no other fittings any types of couplings, except for a listed reducing bushing used on the boundary seal. So here we see a pictorial where the boundary seal is located on the non-hazardous side and one where it's located on the hazardous side. Providing that I meet my criteria within 10 feet, no other fitting except for the reducer, I'm in good shape with both of those as far as being a proper installation. Now, the boundary seal does have some exceptions. In Class 1, Division 1, there's this particular exception where if the conduit from a non-hazardous area to another non-hazardous area, completely unbroken through my hazardous area, and I'm at least 12 inches before there's any breaks within the non-hazardous area, I do not have to put a boundary seal here. There's nowhere for the gas to be able to migrate into the conduit here. There's no threaded openings, no couplings. So I wouldn't have to have a boundary seal. Now, this is also true in Class 1 Division 2. Class 1 Division 2 also has an exception when you have conduit transitioning to cable tray. It also has an exception where you would have conduit that's transitioning from a type Z purge unit. And then we have exception number 4, which is a very common exception because this is an outdoor exception. And a lot of our hazardous locations, when you think about refineries, chemical plants, and you have the different wastewater treatment plants, in that particular scenario, you're in a situation that if the area is a Class 1 Division 2 area, if the conduit does not pass through a Division 1 area with any couplings or unions or fittings, it's entirely outdoors, it's not connected to that process application, and it's above ground, and it's all metal conduit, I only have to seal at the very first unit. I don't have to seal again after that. I did see a question come up as far as sealing between 2 units, and that's normally a slide I have, so I apologize if that slide somehow may have gotten hidden. But to answer that particular question, if I have 2 explosion-proof units, traditionally you would think they each require a seal. But if those 2 particular units are 36 inches or closer, I can put one particular seal in the middle, and now I'm within 18 inches of that particular unit for each one. So that one seal would do just. If I move those units further apart, say 4 feet apart, for example, now I need a particular sealing fitting within 18 inches of each of those particular units. Also, one sealing fitting does not protect a line of equipment. So if I have a switch, I'm going to seal entering and exiting that switch. If that conduit then leads to a motor starter, I'm going to seal entering and exiting that motor starter.
Do you want me to ask you, go through a couple more questions here?
We certainly can. Mm-hmm.
Okay, so I have a table, Eddie from WebEx, from our WebEx, Eddie whatever, Eddie. Table 500.8 T codes, AITs, and surface temperatures. According to the NFPA, there isn't a direct relationship between 80% of the AIT of gases and vapors. Logically, it would make sense that equipment with a T code on the nameplate would automatically be assumed to not have a surface temperature greater than 80% of the AIT of the gas or vapor involved. Any insight from a manufacturer point of view?
What I'd like to do, if it's not minded, is when I discuss lighting, we'll be discussing temperature ratings with that and how their temperature ratings are taken, what they mean. So I think that might help answer the question, but if it doesn't, we can certainly circle back and repeat that question to make sure that we covered all the aspects of it.
Okay, let me ask another one here. It says, can multi-conductor cable be installed through the seal fitting without separating each conductor?
I guess my question for that is it open cabling or is it cabling that is put inside of conduit?
That's a good question. I'm not sure. This was from
Yeah.
Nemanja Pupic. I don't know if you want to,
Okay.
if she,
Okay. Well, I'll tell you what. How about if I address it both ways then?
perfect.
If it's open cabling, what's going to happen is you're going to have a cable gland, and that cable gland is going to act as the sealing fitting. So the sealant in that particular case will be in between all the conductors and not allow the gas to travel through that cable core for gases that can transmit or for cables that can transmit gas and vapors through the cable core. If you're installing it in conduit, which I do see applications where people install the cable within a conduit, here you're in a scenario where when you just read the code at face value, it tells you that you need to separate, remove the jacket and separate those conductors. But obviously, that's not always really practical, especially if we think about things such as variable frequency drive cable that gets a little sensitive if you start playing with its insulation. So what the National Electrical Code does allow me to do is if I can have an approved sealing method within the enclosure, and that's all it says is approved sealing method. In that particular case, what I recommend for people as approved sealing method is the same epoxy that you would use with the cable gland that stops the gases from entering the cable core, you would use that. So when that cable is my conduit and enters the enclosure, inside the enclosure, I would separate the particular conductors and put that epoxy in between the conductors. That's going to stop any possible gas from entering in that cable core. Once I do that, the National Electrical Code will allow me to run that, for example, MC cable through my sealing fitting as if it was one conductor. Also, if I have, like those data type of cables that are real tight and they're not capable of transmitting gases, when they're running conduit, they can be run through as one single conductor. We also have a seminar that discusses cabling in hazardous location areas and touches on some of these subjects much deeper.
So can you just, I mean, you mentioned a couple times you have seminars and things like that. I know that
Sure.
you handle the eastern side. Can you just give an overview from a Cross Heinz perspective? If somebody on this program was like say an Electrical Training Alliance or a JATC or was a customer, how would they get something like that locally, either at their facility or is it over the online? Can you just elaborate on that?
Uh, I would recommend that they contact the local Kraus Heinz person. Now that local Kraus Heinz person may or may not be certified to provide the CEU PDH presentations. Not everybody is. Actually, there's just a few of us that are. But for those that are in another area of the country, if you contact your local person and they're not capable of it, if they'd like to tell that person to contact Bob Potter, I can then hook them up with what would need to be either done or who would be the closest local person that could provide that particular presentation.
Perfect. I got three more little questions here.
Sure.
We're at 127. So Mr. Facto asks, when do you need to split the jacket of a cable slash cord in a seal to seal the individual conductors, and when are you permitted to leave the cable slash cord jacket intact within the seal?
Okay. And that starts to go a little bit with what we were just discussing. The first part of the code will tell you that you have to take off the jacket and separate the conductors. But then it goes into an exception where they allow you to use the approved sealing method within the enclosure. And again, the code just says approved sealing method. That's why I recommend using the same epoxy that works for the cable gland seal to prevent or minimize the gases from migrating through the cable core. And then once you do that inside the enclosure, you've stopped the only place where the gas can enter the cable core. It's pretty much you dammed the beginning of the tunnel. And so because of that, now you have this jacketed cable that gases aren't going to be able to permeate. And so you can run that cable through the ceiling fitting as if it was a single conductor.
Excellent. All right. I think you already got this next one. It talks about speaking to the seal between two NEMA 7 enclosures. Is that the one you answered first when we got into
Yes.
this?
Yes. Yeah, because I did notice that one pop up.
Okay, so the last one I have, at least I haven't been watching as you were talking here, but it says if the nipple joining the two NEMA 7 enclosures is longer than 18 inches, a seal is needed in between. I guess it's a comment. Is that accurate?
If the nipple is longer than 8, yeah, in other words, if you have a nipple or you have a raceway of conduit, I believe the answer to that would be yes. I know there's another, I'm sorry, yes, that'd be 100% true. I'm sorry, for a second there, what was jumping into my head was a fill rate went with the 24 inches that allowed you exception, and I almost confused that for the ceiling fitting. But yes, if your nipple or your piece of conduit is longer than 18 inches, you must have another ceiling fitting.
All right, perfect. So I haven't looked at all this yet. So, but if you want, I can let you continue, and then I'll look through and see if I can find any other answers here. So just give me a second.
I just saw a thing pop up saying you need a seal between two enclosures, no matter what the length, and that is not an accurate statement. In fact, within the National Electrical Code, they actually talk about if you have 36 inches or closer, you may put a seal in between them. So I just wanted to make sure that there wasn't some confusion there. This particular slide is the slide that we had discussed where your ceiling fitting, your normal ceiling fitting is a 25% cross-sectional, and to have an expanded fill ceiling fitting, that will give you the 40% cross-sectional. So in this particular case, these are examples of the expanded fill ceiling fittings. And essentially what happens is the hub size is the size you need and the body is bigger. And that's to allow you to make sure that you have room to be able to separate those conductors with the fiber and get the we already started to allude to this to a certain extent, but when I have open cabling, when I'm going into Class 1, Division 1 enclosure, that cable is required to be sealed. So my gland is actually going to be a sealing gland. So I'm required to seal all terminations in Class 1, Division 1. In Class 1, Division 2, if I'm going into the enclosure that's required to be explosion-proof, such as the motor starter, the circuit breaker, again, that's going to be required to be sealed, and I need to use the sealing fitting again. But if I'm entering an enclosure that's not required to be explosion-proof, such as my terminal box, then I'm just going to use the gland that has been approved for that particular cable or application, and that gland does not have to be a ceiling fitting gland. We also have factory sealed. So here, when I'm factory sealing, I'm going to put the sealing, it's going to be integral to the product. So we see some factory sealed contact blocks. Here's a sealing well that makes the product factory sealed. And this is going to eliminate, except for a couple exceptions that you might find, the requirement for the external sealing fitting. You may also find times when a circuit breaker might have an housing around it, or you may find that it's encapsulated. You might find lighting fixtures, luminaires that are factory sealed, or when I have a piece of equipment that has my terminal housing and my housing that's required to be explosion proof, here you'll have factory sealing done between those two areas. Now, something that's not written in Chapter 5, that's not actually a hazardous location seal, but something that I do see come up semi-often, or periodically maybe is a better word, is condensation sealing. And here, the National Electrical Code requires me, if I have a raceway that is subject to temperature differentials, I need to make sure that I seal it. And I seal it that those temperature differences can't form condensation. An area where I think I've probably seen it the most commonly is wastewater treatment plants. And so there's times where they'll have stanchion-mounted lighting fixtures installed, and there's times when they'll actually bring the conduit up the sidewall that contains the pool of water. So within that cement, it's going to be very, very cool. Where my lighting fixture is heating up, obviously that's going to be a warm temperature. And I've seen where the condensation will collect within those lighting fixtures because it wasn't sealed between the differences of those temperatures. Now, electrical putty can be the seal. It does not need to be an explosion-proof sealing fitting. When it comes to an area with NEMA 7 explosion-proof, we're looking to prevent this particular situation. Now, into the protection techniques of purged and pressurized and intrinsically safe, when I'm looking at my purged and pressurized, here I'm effectively removing the fuel leg of the ignition triangle. And what I'm doing is I'm putting in an inert gas or air into the enclosure to make sure that I can't have an oxygen and gas mixture. An example would be June of last year, I got a call for an explosion-proof closure. Person said I need a NEMA 7 explosion-proof closure. I need to be 48 inches by 48 inches by 24 inches deep. Good luck, because one of those is this. So that's a perfect example for the purged pressurized application. If one of those enclosures did exist, they'd probably be close to 2,000 pounds, just to give you an example. And that's if it was made of copper-free aluminum. So in those types of applications, or some of these different areas, we're going to have equipment that is purged. So when I'm looking at purge and pressurized, I have my X, Y, and Z purges. The X purge is when I have a Class 1 Division 1 or Class 2 Division 1 area and non-hazardous equipment is inside. The X purge is required to be interlocked, that if I lost my purge, automatically all the electrical equipment would shut down. And the reason for that is this would be like putting an everyday general purpose rated switch inside a Class 1 Division 1 area. And that, if you lost the purge, it would be no different than doing that, putting a NEMA 1 safety switch inside that area. So that's why it's imperative that when you lose the purge, all the electrical equipment shuts down. My Y purge is when I have a Class 1 Division 1 area and I put in Class 1 Division 2 components. And my Z purge, the most common, is when I have a Class 1 Division 2 area and I have non-hazardous components inside. Now with Y purge and Z purge, the interlock is optional, but I do need to have some type of signaling to let me know the purge has been lost. And as you can see here, NFPA 496 gives you the information that you would need to further look at purge and pressurized equipment. And when it comes to intrinsically safe, here I'm effectively moving the ignition leg of my combustion triangle. This is going to be typically instrumentation, those things such as 4 to 20 milliamp, 24 volts. And when I have current and voltage that are that low, where they intersect falls below the ignition curves of the particular gas groups. But what I have to prevent against is some kind of fault that could introduce more energy, and then that energy exceeds above the ignition curves, which means it could be ignited. So what I'm going to have is an intrinsically safe circuit that will contain a barrier. And this particular barrier is going to bleed the excess voltage off through ground through the Zener diodes, and it's also going to have a resistor to keep the current where it belongs. Also, there's isolation barriers, which are also called line conditioning barriers. This particular unit that we're showing here is called a Zener barrier. So there's some different types of barriers that can be used in intrinsically safe. Now, when it comes to my field devices, if these devices can generate and store energy, and here's just a few examples, that device within itself also has to be intrinsically safe and rated, because we have to make sure that this device does not become the ignition source. You'll notice here this gland, light blue. Light blue is a common color that's associated with intrinsically safe wiring. Now, when it comes to temperature ratings and my hazardous location lighting, here, I'm not only going to be concerned with class, division, and group, I'm also concerned with temperature ratings. Now, T1 is my hottest, and T6 is my coolest. So if heptane has an auto ignition temperature of 204 degrees C. So for that piece of equipment to operate safely in the area with heptane, I need to have a unit that is T3 rated. Because if I had a unit that was rated T2D, under worst case scenario, that piece of equipment can get up to 215 degrees C. As it passed by the 204, the heat alone, without any contacts opening and closing, could cause the heptane to explode. The T3 that we see here, under worst case scenario, gets up to 200 degrees C. So that would operate safely in that particular area. Now, the fixture here that we see on the left is the explosion-proof fixture, the Class 1 Division 1 fixture. My fixture that we see on the right is not explosion-proof. It's hazardous location rated. It's Class 1 Division 2. It's also the type of design that we would normally see in a Class 2 combustible dust application. This fixture will contain an explosion. So when I have my temperature ratings, I'm taking it on the hottest point externally, because this particular unit, if the gas were to get inside, then it'll contain the explosion. So I really don't, for lack of better words, I don't care if the gas gets inside. Now, I'm not trying to trivialize gas migrating in, but in a Division 1, we assume that's happening. So if something inside the fixture is too hot, that fixture is going to contain the explosion, cool the gases, harmlessly release them back out to the atmosphere. Now, my Division 2 fixture, here I'm taking my temperature rating on the hottest point internally. And the reason I'm doing this is not a fixture that contains an explosion. It's hazardous location rated. It's designed with construction that'll put up with the abuse, with the rugged nature of a hazardous location area, the corrosive elements. It's designed that if something breaks inside, it can't escape. And it's designed that when gas, if it were to migrate inside, nothing inside the unit is hot enough to ignite those gases. Now, I think I remember a question also when we were discussing temperature ratings, when I had asked to hold it to this point of the presentation, talking about the 80% rule. What the 80% rule is that if I have a unit that its heat exceeds 80% of the auto ignition temperature of a particular gas, then I need to do one of two things. I need to use my Class 1 Division 1 lighting fixture, or I need to use a unit that is clearly marked to operate with those particular temperatures. And so that's where that 80% rule comes into play. Typically speaking, I don't usually find anybody taking advantage of the 80% rule if the gas doesn't achieve, because then you'll need to know what those surface temperatures are of that particular unit. So in Division 2, usually I always see clients, with rare exception, use the rated Division 2 fixture because it has all those temperature markings on it that you don't have to worry about those yourself. Other considerations, and we started to talk a little bit about this earlier when we were talking about our standard temperature ratings. Anytime I'm in excess of 40 degrees C, it needs to be marked. When I have lighting fixtures, those lighting fixtures, as luminaires in a hot area, are not going to dissipate the heat as well, so it's going to affect my temperature. Simultaneous presence. When you see a unit that says Class 1 and Class 2, that means it's good for either Class 1 or Class 2. But if I have an area where the gases and vapors are present together in that, then I need the unit to be rated simultaneous presence, because again, that particular fixture with dust coating on it is going to be affected as far as its gas temperature rating. It's like putting a winter coat on it. And this is the temperature markings that I had mentioned earlier that had to have the TA or the TAMB if it's outside of these, and then note those particular operating temperatures outside of this range. So here gives us an example. Remember, the closer you are to T6, the better. The closer you are to T1, the hotter. T3 temperature rating. 55 degrees C, T2D. Temperature rating as I go along. Under simultaneous presence, yes. Okay, certainly. So at 40 degrees C, my temperature rating is a T3. When the air gets warmer, my fixture's not dissipating the heat as well. So at 55 degrees C, my temperature rating isn't quite as good as a T2D. And at degrees C, again, the air's a little warmer. My ambient air's warmer. I deeply apologize for that. One of the side effects, I guess, of the COVID-19 and the requirements of working at home. So at 65 degrees C, we're in a situation where we lose a little bit more of our temperature rating, and it's T2C. Now, when I'm looking at simultaneous presence, here in this particular case, something just popped up my screen, sorry about that. So when I'm under simultaneous presence, at 40 degrees C, my T3 rating now becomes T2B. It's not quite as good. At 55 degrees, I'm still at T2B, but it's not as good as it was when it was T2D. And I've lost my 65 altogether. So, and again, I apologize for that background interruption. Now, the code also has an exception that we see listed. This is a little different than the IEC world. In the IEC world, we're used to seeing temperature ratings marked on everything. But in our National Electrical Code, if the maximum temperature doesn't exceed 100 degrees C, we're not required to put a temperature rating on that particular product. You'll see this typically junction boxes and fittings because they're not going to exceed 100 degrees C, so they won't have a temperature rating on those. Now, another question comes up, do I need to seal these particular luminaires? Well, if we think back to my 4 square, these are not arcing sources. They're really glorified junction boxes. Now, yes, they have the socket wired inside. If it's an HID, they have the ballast wired inside. But really, they are glorified junction boxes that happen to have a lens where the light can exit. You know, it's going to have a driver if it's an LED. So in this particular case, in my Class 1 Division 2, that's why this unit doesn't have to be explosion proof. It falls down here. So with this particular unit, Class 1 Division 2, I'm not required to seal that unit. It's not containing an explosion. It gets me no further integrity. When I'm in Class 1 Division 1, The answer is maybe. And here's why it's maybe. You remember this slide we talked about before. Now, with this particular slide, I mentioned on the bottom, when I have a Class 1, Division 1 housing that's containing splices or taps, I need to seal conduits 2 inches or larger. The code has one other piece of verbiage that goes along with that. If the unit can heat up and exceed 80% of the auto ignition temperature of that particular gas, then all conduit need to be sealed, not just 2 inches above. Is a junction box normally going to heat up like that, where it can exceed 80% of the auto ignition temperature of a particular gas or vapor? I can't imagine. I've never seen where it has happened. So at least not in my experience. That doesn't mean it hasn't. So that's where I would be 2 inches and larger. But what could be a product that could heat up? Luminaire. So in this particular case, if this luminaire could heat up and exceed 80% of that auto ignition temperature, then I would have to seal all entries, not just 2 inches or larger. That's why sometimes you'll see manufacturers have factory sealed as an automatic feature that comes with these particular units. For manufacturers that don't have factory sealed as a feature with the unit that's standard, you need to read their instructions that'll tell you if you need to seal that particular unit or not. This is one that we had discussed previously with the quiz, where I have to protect against my lateral displacement anytime I have 12 inches or longer of a pendant. The whole thing here is if something were to come by and hit that conduit, the conduit could spark, cut a conductor, which can arc. So here's where I was referring to the permanent effective brace coming down to within 12 inches of where the pendant stem connects to the fixture, or where we have flexibility within 12 inches of where the pendant stem connects to the junction box. This flexibility in this picture happens to be the junction box with the flexible hanger with it. Usually these flexible hangers give you anywhere from 11 degrees to 20 degrees of movement, depending on the particular design. When it comes to hazardous location plugs and receptacles, if you think about when we unplug the toaster or the iron in the morning, that spark that we get, or that little blue flash, would be bad in hazardous location. So here we have interlocked units which don't allow us to engage or disengage under load. We also have dead front units, and this is an example of a unit that's a convenient unit, that convenience outlet, that when I put the plug in, nothing happens. It only goes in part way. I flip a switch here, and then the plug goes in the rest of the way. When I want to disconnect, I pull the plug and it comes out part way, and then I rotate the switch back, and the plug will disengage. Everything has been contained inside the unit. This particular receptacle here is an explosion-proof Class 1 Division 1 receptacle. It is not certified for Class 1 Division 2 and would be a code violation. I'm sorry, it's not certified for Class 2. Somebody's been talking too much. It's Class 1 Division 1 receptacle. It's not certified for Class 2 combustible dust. This particular unit here, the dust would interfere with the switching mechanism here. So that's why it's not certified. So this unit's approved for Class 1 Division 1, Class 1 Division 2, but would be a code violation to use it in a Class 2 area with combustible dust. Gets back to what we talked about a couple times earlier. Just because a piece of equipment is explosion-proof does not mean it's approved for all areas. Additional equipment that you might find in hazardous location areas: horns, strobes, speakers, motor starters, panel boards, disconnects, control stations. Cable glands. If we're having open cabling, we're going to find a lot of cable glands. If I have a Class 1 Division 1 unit, it's going to look something like this, or some type of configuration similar to this with all of the bolts. Class 1 Division 2, if it's housing an arcing source, may be some type of similar configuration, but if it's Class 1 Division 2, just a splice box or terminal housing, now I'm just worried about my environmental protection, and so I may just have a stainless steel or fiberglass unit. Where to look for more information? National Electrical Code, API 500, NFPA 497, third-party certification people such as UL. Manufacturers have technical documents. So if you're concerned about how many conductors of what particular size can I fit into a trade size of a conduit body, they'll have documents that'll guide you in that direction. Also, manufacturers will have bending radius and cubic inch capacity charts that will guide you. Also, instruction sheets. They're going to give you detailed instructions of how to comply with the code. When you're looking at products that require temperature ratings, you're going to see temperature ratings broken down by not only the certification for that particular product of the area it can be installed, but also by the ambient temperature. You'll also see manufacturers' catalog pages with additional certifications. And then, of course, you can always go online to the third-party certifications and check a manufacturer's certificate. And I saw a quick question come up. Do all the bolts have to be installed? Yes, they do have to be installed. And when you have the smaller control stations, those ones just need to be hand tight. When you have the larger junction boxes or motor starters or panel boards, typically with those, you'll see manufacturers have torque ratings for those. So they'll have to be tightened to the proper torque ratings. Usually those torque ratings, and it can vary per manufacturer and type of box, but they're usually going to fall somewhere around that 50 to 55 pound of torque force. And that's our presentation. So I guess we can open back up, see if we have any questions that have come up since the last time we answered questions.
Oh yeah, I got some good ones here. So I'm gonna
great.
I'm gonna walk down through them. Okay, so David Platt had two good questions, and they're both related to like a single-family dwelling unit. So his questions were: would you consider a sewage tank? Actually, it's one question. Would you consider a sewage tank at a single-family site as a classified hazardous location per the NEC?
At a sewage tank at a home, a residential home?
Yes.
That's no, I wouldn't. But then again, I'm not the authority having jurisdiction, but I cannot say that I've ever seen when people have sewage tanks that they have been classified.
Okay.
A lot of times the rules are a little bit relaxed, for lack of better words, when you're talking residential dwellings, because they're not large, facilities, production areas that are going to have large volumes of these particular gases and vapors or combustible dust potentially available.
All right, hold on. Let me get the next one here.
Sure.
It says, okay. It says, what do I do if the equipment is going to be used in temperatures are below 25 degrees C? And how do I get the equipment approved for use in lower temperatures?
What if you have an area that is a lower temperature area, lower than negative 25 degrees C, then you need to make sure that that particular equipment is certified for that. So you're going to need to check with that particular manufacturer to see if they have certifications for less than negative 25 degrees C. And as we had mentioned before, the UL 1203 test, which is that 4-time safety factor test, the hydrostatic test, the 4 times that amount, when the temperature exceeds negative 25 degrees C, the test becomes a 6-time safety factor test.
Just give me a second. I'm going to open up my Mentimeter code and share that with everybody so that I'm going to put it on this since I'm not sharing my screen. I'm going to say menti.com exit code is control V 24.
Would you?
Hold on one second. Let me go
I was
ahead.
going to say I can give you sharing back if you'd like. Now that we're done.
Yeah, that would be good. That'd be good.
Okay, sure.
Actually, you don't have to. Don't worry about it, Bob.
Okay.
Don't worry about
All
it.
right.
What I'm doing now is I am showing for those on YouTube. I put the Menti code in the chat box for the WebEx guys, and I've got the Menti code showed for my YouTube people, so everybody should be covered. And your image and my image is both on there, so while we go through these questions, they can see something. So.
Okay, perfect.
Wendell Whistler asked, well, what do I do? Oh, wait. Oh, you already did the minus 25, right?
Correct. Yes.
Okay. Jimmy Guerrero, not sure if addressed before, but would you comment on factory sealed versus hermetically sealed pros and cons?
Sure. And there's a difference between the two. Factory sealed would be some of the examples that we had showed on some of those slides, like that factory sealed sealing well, the factory sealed contact block. Hermetically sealed is going to be more of a fused a unit where the parts are fused together, and hermetically sealed is actually a Class 1 Division 2 product approved by itself. Now, if you want to use that in it's in Class 1 Division 2 approved by itself. If you want to use that in Class 1 Division 1, it would have to go inside of that particular explosion-proof NEMA 7 enclosure. But they're really a little bit different methods. You see a lot more factory sealed or encapsulated than you do hermetically sealed. And so, like, for example, the factory sealed contact block could have air get into that contact block, but the area is so tight where the contacts open and close, you couldn't have a mixture that's going to have an explosion. Where the hermetically sealed, you can't. It's not. There's going to be no air getting into that because of the fused brazing that seals it.
Okay, so here's another good one. Why is the 12-inch pendant rule applicable for hazardous locations? This is coming from YouTube.
Sure, and the concern is that if you have a pendant hanging down, let's just say you have a pendant hanging down 3 feet, and somebody comes by with a piece of equipment and hits the fixture, now it's going to start to move. And if they're not paying attention, it moves real far. You run the risk of the conduit sparking or the conduit actually cutting a conductor, which could create an arc, and that could ignite my gases or ignite my combustible dust in suspension. So that's why we have to make sure that we protect against that lateral displacement.
Would that apply to anything? Like if you had anything that was hanging down that could be free floating? Is it just a lighting fit? Like if I had a cable tray or something like that was hanging down.
I'm sorry, what was your example?
Like a cable tray.
Well, the cable tray isn't really just going to hang. That's going to be more of a solid installation. You know, it's going to have its proper supports because the cable tray has its requirements for being supported, you know, every so often, support at the splices, all those different types of things. So you're going to be in a situation where that's not something that if somebody hits it, that's going to be more like a mashing of it as opposed to making it start to move, you know, and bend and move along like a stick of conduit could.
All right. I was just answering a question here. So another one. Mr. Oscar Commando from YouTube asks, I have a case where a room is classified as Class 1 Div 2 and has a motorized roll-up door, does the motor / equipment that controls the door, does that need to be classified?
So when you look at motors in Class 1 Division 2, typically your like totally enclosed fan cooled motor, for example, that is approved for Class 1 Division 2 area. That motor doesn't have to be rated. Okay, so there is verbiage in the code that talks about when you're required to have a rated motor, the Class 1 Division 1 having the rated motor, the sliding contacts, things like that. But typically your totally enclosed fan cooled motor, and there was a time when the code actually called out totally enclosed fan cooled, is perfectly fine for a Class 1 Division 2 area. Now, the control station for making that door go up and down, that if inside the Class 1 Division 2 area will need to be certified for Class 1 Division 2. That may be the NEMA 7 explosion-proof housing, or it may be a non-metallic housing or stainless steel housing in which the devices are factory sealed or encapsulated.
All right, so we got another one from Bill Neitzel. Tom, would be interested in a Class 2 seminar as it pertains to farms, feed mills, and the like. So Bill's asking for possibly doing a Class 2 seminar in those types of areas. I don't know if is that.
I'm sorry. What type of areas were they again?
Pertaining to farms, feed mills, and similar areas like that. Is that in your wheelhouse?
We do have the Class 2 certified presentation, and the Class 2 sort of presentation is going to cover all the different areas. When we're talking feed mills and those types of things, that's going to be covered under the Group G portion of the presentation. But the presentation will also discuss my metallic dust, and it will also discuss the carbonaceous dust.
Awesome.
The group G is more what sometimes people refer to as organic dust, which is going to be, the foods, the flours, the sugars. It's going to be the fine pharmaceutical ingredients. It can be plastics. It can be the sawdust from wood. Some of those types of things.
Yeah, I know it got like grain mills and stuff like that can be very dangerous, and I've documented a lot of explosions.
Extremely dangerous, and we're still killing people on a regular basis yearly with these Class 2 areas because people just aren't familiar enough. In fact, OSHA put together the National Emphasis Program back in 2000, and that became effective in 2008 to help people better recognize, including their own organization, the danger of Class 2 combustible dust. Look, you think about it, 2008 really is yesterday in our electrical lives. This isn't like somebody telling the stories of 1950, throwing the knife blade switches and all those kinds of things. 2008 is really, really close.
Yeah, I agree. All right, so there's another one here. It says, earlier I saw a chat comment stating that oversizing a 25% fill seal off and using reduced bushings was a cost-effective way of avoiding the added cost of a 40% fill seal off. Is this statement correct? And he believes that one of the slides contradicted that chat statement. Can you any comment on that?
As far as cost-effective, no, because it's a scenario that if you have the expanded fill ceiling fitting, that's going to be a ceiling fitting that's going to arrive to you with the proper size hubs and the larger body. If you want to make up your own 40% fill seal, effectively you have to jump up a size in the ceiling fitting. It may be one size, it may be two sizes, depending on the particular fitting to achieve your 40% fill rate. And then you'll also have to procure the reducing bushings. There was a time when this was actually a common practice for the 40% fill rate. People would upsize one or two ceiling fitting sizes, put in the reducing bushes, you take them back down to the conduit trade size they have, and that's what they used. Now the code actually tells us ceiling fittings are approved for 25% fill rate unless it's specifically identified for a higher fill. So in that case, you could make the argument that you must use the expanded fill ceiling fitting and couldn't make up your own. But I also have seen where the authority having jurisdiction has been perfectly fine with the person using the oversized ceiling fitting and then putting in reducing bushings, like an RE reducing bushing, the hazardous location rated reducer, and making up their own oversized. So it's not out of the question to be able to still make up your own as long as the AHJ, approves that. But as far as cost, you're not really going to have. It's going to be 6 of one, half a dozen of another when you start looking at those products. In fact, probably making up your own might be a little more expensive because you have to get the reducing bushings.
All right, I got one from our WebEx here. So it says, what about Chris Valtiera? What about the process of milling for microbrewers? They are arguing that they are cracking the grain rather than milling. Any comments on that one?
No. That is really an argument that is going to be the person classifying that area and the authority having jurisdiction in that area. But after all, but really what it comes down to is when you have the grain and you have combustible dust, you start with a combustible dust is going to be a fine particle. It's going to be able to, it's 500 microns or smaller, fit through a number 35 sieve. So these are some of the things you're usually talking about, much smaller type of particles. Now, I don't know when they say they're cracking, what that does to the size or what that does to any particles that can go in suspension in those particular areas. But another thing that you have to be concerned about with these particular applications is dust that can dehydrate or carbonize, because when they dehydrate, if they sit on top of an item that can excessively produce heat, then it can catch fire. So that's why when you have areas with group G, a lot of times like a portable floodlight that can be taken into those areas may have restrictions on how high you can point that upward, because if the dust that could dehydrate, which I think some of those are those types of dust you would see in a brewery, sit on that lens where that heat's coming through the lens for the illumination of light, it's going to get extremely hot and could cause those dust to catch fire.
I think what we will have to do is go do some investigating at a brewery. So, but I got one more for you. How do you recognize a rated RE bushing?
With the RE bushings, you're going to find that the larger sizes will have it marked on them. Once in a while, you'll find a small size. It may be difficult to get the marking on it, but typically they should be marked on the unit. Now, if you're asking after it's been installed, makes it a little bit more difficult.
Okay, and here's one from YouTube. Where are the location requirements for intrinsically safe interface devices?
A lot of times what will happen is when you have intrinsically safe, you're going to have the part of the equipment that's in the non-hazardous area that might be taking reading, and then they're going to the devices. So you're going to have devices and what have you in your hazardous area, and then they're sending back the readings or what have you to your non-hazardous area. Now, that doesn't mean that you couldn't have things such as interface cards and what have you located in your Class 1, Division 1 area. And typically when that happens, you're going to have the NEMA 7 enclosure housing those. But more times than not, you're going to have cables or circuits that are communicating between the non-hazardous area and the devices that are in the hazardous area. idealistically, it would be that you want to try and keep, a lot of those particular pieces out of the hazardous location area. Even the barrier is better located out of the hazardous location area.
All right, I got a few people asking for your contact information. How do you want to handle that, buddy?
Certainly. Yeah. My email is Bob C. Potter at eaton.com, and that's Bob, B-O-B, the letter C, Potter, P-O-T-T-E-R, at eaton.com.
Well, that was easy. Awesome. Well, you're getting a lot of kudos. You got outstandings from a lot of different people. Everybody's enjoying the material, which I think is great. We're
outstanding.
We're at.
I'm glad.
Yeah.
I'm glad they're enjoying it.
Yeah, I am too. I learned a lot. I've been focusing on all of these. The chat session has been great. I'm gonna look at WebEx and see if there's anything new. I have another meeting at 15, so I shared the. Yeah, it's Bob C. Potter at eaton.com, EATON.com. So, and I got the Mentimeter code. Mentimeter code is 240243, and it's Bob C. Potter at eaton.com. So I got that done. Thanks, Bob. Article 504. I'm just reading through some of these chat sessions. Okay, really? I say great session. Okay, so all right, so that's it. So nothing else on YouTube. I'm gonna check Facebook out. Make sure I didn't miss something on Facebook. And I think we've addressed all the questions. And I think we're good to go, Bob. But I really appreciate
outstanding.
I appreciate your help and the sharing your knowledge, and I know everybody else does as well. I was watching the content. We had a little over 200 on YouTube. I don't know how many. We didn't have as many on Facebook, I don't believe, because I really didn't advertise over there as much that I was going to do it there. So, but we had a really good turnout, and I really appreciate your sharing your information.
Outstanding. And I'd like to thank everybody who attended today.
Yes, and I do too. So thanks to everybody out there in YouTube land and on Facebook and on WebEx. Really appreciate your engagement and all of the chats and questions. So on the YouTube and the Facebook, guys, I am going to queue up my exit. And again, hopefully you saw the last Mentimeter code. And have a good, safe evening and the rest of your week. And we'll check out tomorrow. We'll be talking about arc flash calculations. So I'm queuing up the outro. Perfect.
Hey, thank you very much.
Hey, thank you, Bob. I really appreciate your help.
I'll send you an email with the other presentations that, if there's interest in the future.